Let us now look at the next set of exercises on equivalence relations. So the 13th one, here we are given this relation which has been defined on the set of all natural numbers, that is all positive integers, and two natural numbers a and b are defined to be related if their difference is a multiple of 3. That is, if their difference is 3k, where k is some integer. First, the exercise asks if this is an equivalence relation, and if it turns out to be an equivalence relation, we have to figure out its equivalence classes. It is, in fact. We will now show that. Let a, b and c be any three natural numbers. Since a minus a is 0, which of course you can write as 3 times 0, we have a related to a, and that means every natural number is related to itself because a has been chosen arbitrarily, and so this relation is reflexive. Next, let a be related to b. Then a minus b is 3k for some integer k. Now this implies b minus a is 3 times minus k, multiplying both sides of this equation by minus 1, where because k is an integer, so is minus k. So b is also related to a, and so the relation tilde is symmetric. Next, let a be related to b and b be related to c. Then first of all, a minus b, it is a minus b, yes, a minus b is 3k1 and b minus c is 3k2 for some integers k1 and k2. From this we get a minus c. A minus c can be written as a minus b plus b minus c. A minus b is 3k1, b minus c is 3k2, so this is 3 times k1 plus k2. Now because k1 and k2 are both integers, k1 plus k2 is also an integer, where k1 plus k2 is an integer. Thus, so we have shown that a minus c is also an integer multiple of 3. So a is related to c by the definition of our relation, and this is transitive. Hence, tilde is an equivalence relation on the set of all natural numbers. Okay, so now it's an equivalence relation. Now, what are its equivalence classes? That we do in that we find in the next paragraph. Note that the equivalence class, because we are dealing with positive integers, so the equivalence class of the relation that contains 1, what by definition what is that? It consists of all natural numbers a such that a is related to 1. That means it consists of all natural numbers a such that a minus 1 is equal to 3k for some integer k, or stating this whole thing in a slightly different manner, it is the set of all natural numbers n which are of the form 3k plus 1, where k is an integer, and this can be written more compactly like this. It is the set of all natural numbers 3k plus 1 such that k is an okay. Now, because a is a natural number, so a cannot be negative, also a cannot be 0. So now you cannot actually take any k. It looks like we have taken any k here, but actually that is not the thing. You see, this is the set of all natural numbers which are of the form 3k plus 1, where k is some integer. Because a is natural, that's where we start. So k cannot be just any integer. The minimum value of k will be 0. So that's why when we are writing this set more compactly like this, we have to take non-negative integers. K is a non-negative integer. K is either 0 or positive. When k is 0, the corresponding element is the natural number 1. So this is one equivalence class, and it's in fact that particular equivalence class which contains the member 1, which contains the element 1. Similarly, the equivalence class containing 2 can be shown to have natural numbers that look like this, where k is a non-negative integer and the equivalence class containing 3 consists of all natural numbers that look like this. K is a non-negative integer. Now in this particular case, because you can take 3 common out, so this will be 3 times k plus 1. Now if k is any non-negative integer, in place of k you can think of another variable, or rather this what I am trying to say here is this: in place of this set you can write, again we will have the same set but represented slightly differently. 3 times, to distinguish this k from the other case, you can write 3 times m, where m is a positive integer. Do you see why this set and this set are the same thing? You take any element in this set, it looks like 3k plus 3, where k is any non-negative integer. That means that 3k plus 3 is actually 3 times k plus 1. Now because k is non-negative, k plus 1 is a positive integer. So that means that 3 times k plus 1 is actually is of the form 3m. So that element belongs to this. And if you choose an element from this set, then it looks like 3m, but that 3m of course you can write as 3 times m minus 1 plus 1, or 3 times m minus 1 plus 3. Now because m is a positive integer, m minus 1 is a non-negative integer. So that means this is of this form. So that element also belongs to this. So these two sets are actually, each one of them is a subset of the other, and so they are equal. Okay, so we have, see what we have done so far is we have written 3 equivalence classes. Now we claim that actually these are the only equivalence classes. We have to prove that, however. First, let us try to see that these equivalence classes are distinct. Equivalence. Suppose, but that is almost evident, no? Because of the nature of the general element in each such equivalence class. Almost evident. Why I am saying it's because any element, for example, in this class looks like what? It looks like 3m. so that element is divisible by 3. However, any element here or any element in this class, none of them is actually divisible by 3. Elements here leave the remainder 2 when divided by 3 because of their structure, and elements here leave the remainder 1 when divided by 3. So class 3 is different from class 1 and class 2. Are these two things the same? No. Again, because of a similar reason, any element in this class, class 1, leaves the remainder 1 when divided by 3, and any element here leaves the remainder 2 when divided by 3. So we can justify their distinctness like this, since natural numbers belonging to different equivalence classes from the above list of equivalence classes. That means from the equivalence classes class 1, class 2 and class 3, natural numbers belonging to different equivalence classes from among these classes leave different remainders when divided by 3. Divided by 3, the classes 1, 2 and 3 are mutually disjoint. No natural number in one of them can belong to any of the other two. So they are mutually disjoint, and because of that reason in particular they are distinct also. So that means they are different equivalence classes. Now we need to show that they are all the equivalence classes we can get. There is nothing else. To show that, we argue like this. Now let A be any natural number. Be any element. By the division algorithm, or the Euclidean algorithm. Some people call it the division algorithm, some people call it the Euclidean algorithm. It's nothing but the thing we have been taught from the very beginning of our school days, that when you divide an integer by say a positive integer m, say, then there exists a unique quotient q and a unique remainder r, such that the given integer is qm plus r, where r is a non-zero integer, non-negative integer, and it is less than the divisor m. So by the division algorithm, a is of one of the forms (3k), 3k plus 1 and 3k plus 2. Why? Because we are dividing a by 3. So by the division algorithm there will be a quotient k and a remainder r. Now because that remainder r has to be a non-negative integer that is less than 3, so you get the only 3 possibilities. The remainder can either be 0 or 1 or 2. Okay. Where is of one of these forms means it's understood that k is an integer. Since a is positive, this implies a belongs to this, or a belongs to this class, or a belongs to this class. How does positivity of a imply these things? You see, if a is of the form 3k plus 1, then fine, it belongs to class 1. That's what we have written here. Also, if a is of the form 3k plus 2, then it belongs to class 2. But if a is of the form 3k, then it is here. And in all these things, positivity of a just simply tells us that a, besides having this particular form, is also a natural number. Okay, so that's why we have these things. So that means what? It means that either a is related to 3, or a is related to 1, or a is related to 2, and that's why these 3 are the only equivalence classes. And do you see why we are getting these only 3 equivalence classes? Because from these containments we get this or this or this. In this final conclusion, we have used that property of equivalence classes, that any two equivalence classes are either the same thing, the same equivalence class, identical, or they are disjoint. When they are different, they are different, in the sense that you cannot have two equivalence classes like this, which are not the same and at the same time they have something in common. That will never happen. Either they are both of them are the same thing, or they are totally disjoint. Now the equivalence class containing the natural number a, of course, is this one by definition. And here we are seeing that a already belongs to this other equivalence classes. So that means if you have this, then because the class containing a is not disjoint with the class containing 1, so these two have to be the same class. That's why we have this. From this we get this, and from this we get this. Okay. So and 3 are the only equivalence classes. So this completes the solution. Next, define a relation. Again, a similar question, but the set and the relation, they are different. A relation tilde on this time this finite set, the set of the first 7 natural numbers. Via this rule, A is related to B if and only if this time A and B are both even or both odd. The rest is like before. Is tilde an equivalence relation? If so, what are the equivalence classes? What are its equivalence classes? Although a very small set is given to us, but we will work with general elements. See, the smallness of this set is actually deceptive. Someone may think that they will find all the pairs of elements A and B from this set that are related, first of all, and then with those pairs one will verify reflexivity, symmetry and transitivity, all of them. But that is just a wastage of time. Instead, it's better to just simply work with general elements A, B and C, because although the elements you can see here are only a few, but the definition is a general definition, so we can just use the definition of the relation itself and not the specific elements. So again we consider any three elements A, B and C in the given set. Since A and A, see, if A is any one of these numbers, it is either even or odd. So when it is even, when A is even, then A and A are both even. It sounds silly, but it's just the way things are. Since A and A are both even or both odd, we have A related to A, and so the relation is reflexive. Because of the trivial nature of this statement, some people would simply write it's trivial to see that the relation is reflexive. Okay, then next, symmetry. Let A be related to B. Then A and B are both even or both odd. This implies, again, we are going to write something that is just the same thing that we have here, but in a different manner. That's all. This implies, instead of writing A and B, we will just now write B and A. Are both even or both odd. So B is related to A by the given definition, and thus the relation is symmetric. Next, let A be related to B and B be related to C. Then A and B are both even or both odd, and just like that, B and C are both even or both odd. Okay, so now cases will arise. If A and B are both even, then C must be even because B and C are either both even or both odd. So because B and C are either they are simultaneously even or odd, and it's already we have chosen that A and B are even, so that means B is even, so that forces C to also be even. In this case, A and C are both even. On the other hand, if however A and B are both odd, then we can similarly see that C is odd, because B and C can either be both even or both odd. Now because B has been chosen to be odd, so C must be odd. In this case, A and C are both odd. So that means A and C are either both even or both odd. So by the given definition of our relation, A is related to C. A is related to C, and so the relation is transitive. This is thus an equivalence relation. Okay, now we have to figure out the equivalence classes. Yeah, the smallness of the given set will help us, because we will have to write only a few elements. So you just see what equivalence class each one of them belongs to. That will give you all the equivalence classes. The equivalence classes are, and because we have only a few elements finitely, and that too only a few, so we can write all the elements in the equivalence class. So because the first element is 1, you see what elements belong to this. Two elements are related to each other if either both of them are even or both of them are odd. Now because 1 is odd, so all the odd elements will be related to 1, and we will have 1 of course is related to 1. This is always the case, okay, in any equivalence relation, because the relation is reflexive, an element will always be related to itself, so it will always belong to its own equivalence class. So 1 has 1, 3, 5, and we have more, 7 is also there, and 2, which just has all the even integers, 2, 4 and 6. So that's just it, these two equivalence classes. Next, define a relation tilde this time on the set of all integers via this definition. A is related to B, integer A is related to integer B if and only if A and B have the same absolute values. Is this an equivalence relation? If so, what are its equivalence classes? This also, you can almost see that it will be an equivalence relation. Let A, B and C be any three integers. Since this equation is trivially true, A is related to A, and so the relation is reflexive. Next, let A be related to B. Then but this implies that the absolute value of B is equal to the absolute value of A, and so B is also related to A. Thus the relation is symmetric. Next, and PP related to C, then this and this, which imply so from this last equation A is related to C and thus this is transitive. The given relation is thus an equivalence relation. Okay, now note that so we have proved that it's an equivalence relation. The next job is to find out the equivalence classes. A is related to B if and only if they have the same absolute value, that is if and only if they have the same size, or in other words, if and only if they are equidistant from the origin, or rather equidistant from the integer 0. On the integer line, if you want to call it, you take two integers. They satisfy this equation if and only if they are equidistant from the number 0, because absolute value of A is actually the distance of A from 0. It does not matter what A is or what its sign is, whether it is positive or negative. If you take A equal to 1, then the distance is 1. If you take A equal to -1, then also the distance is 1. That's why we take absolute value. So do you see that in every equivalence class there will be exactly two integers, except for there is one exception. Apart from that, in the other equivalence classes, in each one of them there will be two integers. So the equivalence classes will be these. That is integers which are at a distance 0 from 0. There is only one such integer. Integers which are at a distance 1 from 0. There are two such integers. Integers which are at a distance 2 from 0, and so on. So you can see this is the justification, but we are not going to write anything in detail about that. We will just simply write it is easily seen that the equivalence classes are precisely the following. If you want to argue why it's so, then you can elaborate. Let's write one more, minus 3 comma 3, and it goes like that. So we can see that all the equivalence classes look similar to one another, except this one, which has only one element. So this completes the solution. Then define a relation is it on the set of integers again. So here this definition, two integers are related if and only if their product is positive. So that means either both of them are positive or both of them are negative. Is this an equivalence relation? If so, what are its equivalence classes? Unlike the previous exercises, this one is not an equivalence relation. It almost, it seems like it will be, but it fails to be reflexive, because 0 is also an integer. 0 is here in this set, but 0 is not related to itself. Product of 0 with itself is not greater than 0, it's equal to 0. Note that and 0 times 0 is 0, and that is not greater than 0. So 0 is not related to 0, and thus the relation is not reflexive. One of the three conditions is not being satisfied, so automatically we don't have to look at the others. This is not reflexive means it is not an equivalence relation. this is not an equivalence relation. So the story ends here itself. No question of equivalence classes. Let S be the set of all subsets of the set of integers. In other words, S is the power set of the set of integers. Define a relation. So now we are defining a relation on S, not on Z. On S, via this rule, T is related to U. So T and U are both subsets of the set of integers. If and only if T is a subset of U. Then we have to complete the exercise. Is this an equivalence relation? The rest is same. If so, what are its equivalence classes? Note that, okay, now before we proceed and write something, a few words about this type of problems. Even before you write the solution, you should somehow see in your mind whether the relation is or is not an equivalence relation. If it is not an equivalence relation, then that means at least one of the three conditions is failing. So either it's not reflexive or not symmetric or not transitive, or maybe not more than one of these is true. In that case, there is no point starting with reflexivity. So here, for example, I can see that the relation will not be symmetric. So I will concentrate only on symmetry and nothing else, or rather lack of symmetry. So note that our set is the set of integers and S is the set of all subsets of this. So these are two elements in S. Such that the first one is a subset of the second, but the second one is not a subset of the first. That is, this is related to 1, 2, but this set is not related to this set. So this is not symmetric, and hence not an equivalence relation. So this solution also ends here like the previous one. Let S is like before. Let S be the set of all subsets of the set of integers. But now our relation will be different. Define a relation tilde on S via this rule. T and S are two subsets. Oh, why? Okay, no, sorry, this is not S, this is U, because S has already been taken here. T is related to U if and only if T difference U and U difference T are both finite sets. Show that here we have to show that this is an equivalence relation. Okay, and describe the equivalence class containing the element which is the set consisting of 1, 2 and 3, and the equivalence class containing the set of all even integers. let T U V, okay, let T U and V be three elements in S. That means each one of them is some subset of the set of integers. Since T difference T is the empty set which is finite, we have T related to itself and hence the relation is reflexive. Okay, so it is reflexive. Every set T is related to itself. Next I need ink. Next, let T be related to U. Then T difference U and U difference T are finite. That is, U difference T and T difference U are finite, which is the same statement, but we have just switched the order of these two things. Thus, U is also related to T, and so the relation is symmetric. So reflexivity and symmetry are very easy. Transitivity, however, is relatively more complicated. More difficult to show. I mean, it's not as easy as just simply observing or writing two statements and concluding. Next, let these things be true. Then a number of sets will be finite. T difference U, U difference T, U difference V, and V difference U are all finite. Okay. Let us now guess some things. What is our aim? Our aim now is to show that T is related to V. That means we have to show that T difference V and V difference T are also both finite. Let us now look at these sets. So this is T, this is u and this is v. Okay, our aim is to somehow figure out what T difference V is in terms of these other differences. T difference V by definition is the set of those elements in T that are not in V. That means this part. This is T difference V. Now we can see that T difference V actually is a combination of two regions. One is this region, which consists of the elements that belong to only T, and the other is this region, which consists of the elements that belong to both T and U but not V. Okay, so we are now guessing something. From this Venn diagram, we now show that T difference V is this part which has the elements that are in T only. And how shall we write that part? T difference U union V. From T we have removed U as well as V, and that leaves us with the elements that are only in T, and union this part which is obtained by from T union U and subtracting, oh sorry, this is not union, this is intersection. T intersection U is this much. From that we are subtracting this. That means T intersection U intersection V. This is only our guess because the identity looks fairly complicated. We don't know whether it's true or not. We will now have to prove it if it is true. And we will somehow, once we prove this and we have this at our disposal, we will then use it to somehow prove that T difference V is actually finite. And if we are able to do that, then V difference T will similarly be handled. This is something we are just immediately guessing from this figure. One may write in place of this, that is particularly on the right hand side, an expression that is not as complicated as this. Maybe it has fewer number of steps, but this will get the job done. We will see. So we need to now show that this is a subset of this and this is a subset of this. Without thinking more about what these sets actually are, we straight away take an element here, show that it belongs to this one, and an element here, show that it belongs to this one. So let, or instead of starting with let, we are going to argue like this. Now X belongs to T difference V implies what? X belongs to T and X does not belong to V. Now, besides X being in T and not being in V, simultaneously x can either be in u or not be in u. These are the only two possibilities. So we can write like this: x belongs to t and x does not belong to v, and x does not belong to u, or these things and x belongs to u. Okay, now we will arrange the things a little bit, rearrange them. X belongs to t and x does not belong to v, u and x does not belong to v, or x belongs to t and x belongs to u, and x does not belong to v. Okay, now this implies x belongs to t, and now we see what the situation is. X neither belongs to u nor belongs to v. So x cannot be in the union of u and v because it is nowhere, neither in u nor in v. So x does not belong to u union v, or what happens here, x belongs to t as well as u. So x belongs to t intersection u, and x does not belong to v. Now combining these two things, this statement and this statement, because we have and the structure of this whole thing tells us that x belongs to t difference u union v, or okay, now before we write something here, I mean we change this, let us recognize the fact that x does not belong to u intersection v intersection t. The question is, how can we write this in place of this? X not belonging to v means what? This part is telling us that x is not in v. So that means x lies outside of v somewhere. Now in that situation, can x lie in this region, u intersection v intersection t? Definitely not, because had that been the case, then x would be inside v, but x is not in v, so x cannot belong to this. And note that these two things are not the same thing. This is saying that this must be true. You cannot go back. Okay, if you are given that this x does not belong to this central region, that does not mean x does not belong to v. That just simply means x is not here. X may be elsewhere in v. But since we are going in one direction, so it's okay. Okay, now this implies what? X belongs to t difference u union v, or x belongs to, won't have place to write this. Anyway, we will continue from there. T intersection u difference, because x is not here, difference u, v and t. And this implies this or this. So x is either here or here. So that means x belongs to t difference u union v union t intersection u difference t u v. Whether you write u v t or t u v, you can change the order because intersection of sets is commutative. So that means any element here is actually here in this set. Now we prove the converse. If we need the figure again, we will draw it, a small one, beside our calculations. This is one thing, and say y belongs to this final set. Union t, okay, this is looking confusing, t intersection u difference t intersection u intersection v. If one wants, one instead of writing this intersection, one can also write just simply difference b. That will be the same thing, but let's not think of those things anymore. We just want to finish this. So first of all, writing using just the definitions of these operations, union, so t difference u union v, or y belongs to t intersection u difference t intersection u intersection v. This implies y belongs to t and y does not belong to u intersection v. You can see that here we are actually not doing anything new. We are just doing we are writing all these things in the reverse order. And we won't actually have to do anything except here. Once we reach this place, then we have to think of some things, because this does not imply this. So now this one, y belongs to t intersection u and y does not belong to t intersection u intersection v. When I said this does not imply this, I meant only this x not being in this set does not imply x not being in v. Okay, only that much, not the entire thing. Y belongs to t, and now y does not belong to, I think we have written it wrongly. This is not intersection, this is union. Y does not belong to the union means y is neither in u nor in v. So that means y does not belong to u and y does not belong to v. Or okay, now although I said this does not imply this, but still I am writing and y does not belong to v. how, what is the justification? You see, y is not in the intersection of t, u and v, but at the same time, I am saying because we have and, y does belong to both t and u. So that means y is in t as well as in u. Now if y is also in v, then y would automatically belong to this intersection, but that is not the case. It's given that y does not belong to that intersection of the three sets. So that means y cannot belong to v, and that's why we are able to write this in place of this. Not simply from this, because that is not true, but additionally using this one also, we can conclude this. And now everything has fallen in place, and we can just simply write the things in the reverse order. Y does not belong to u and y does not belong to v, or don't make mistakes with these logical connectives. Okay, you or and, if you write and in place of or, the entire meaning will change. Or now we have this, so which can be written more elaborately like this, and y belongs to u and y does not belong to v. Ideally, from this, when I am writing this, I should have enclosed this first two within brackets, and then I should have written and this outside that bracket, but I have not done that. Is that a mistake? That is not a mistake, because throughout we have and there is a statement or a construct of statements which says that, say P, Q and R are three statements, then this compound statement is the same as this compound statement. When we use and to connect two statements to make a compound statement, we call the compound statement a conjunction, not disjunction. Disjunction is or. So conjunction is associative, and that's why there is no need to put things in a bracket. It's like when you write 2 plus 3 plus say 1. It does not matter whether you add 2 and 3 first and then add 1 to the result, or you add 3 and 1 first and then add 2 to that result. You are going to get the same thing. You are going to get 6. So this is associativity of addition. Like that, conjunction is also associative. Okay, let us now look at what we have got, how far we have come. Y belongs to T and Y does not belong to V, and Y does not belong to U, or Y belongs to T and Y does not belong to V and Y belongs to U. In both the cases, whether this is true or this is true, Y is in T always, and also y is never in V. Now it's a matter whether y belongs to U or it does not belong to U. Depending on that, we have either this is true, or rather either this is true or this is true. So that means in any case y belongs to T and y does not belong to V, which implies y belongs to T difference V. So T difference V is actually equal to what we were claiming it to be, T difference U in union V union T intersection U difference T intersection U intersection V. So what we wanted to prove is now true. Now, so what? Now how can we use this? Now we have T difference V equal to, let us now investigate this new identity we have found, union T intersection U difference now I am going to write something which is like the De Morgan's, like one of the De Morgan's laws, and it can be proved also. What does De Morgan's laws say? They say that the complement of the union is equal to the intersection of the complements. It's also something like that, although we don't have complement here, but general difference. We are taking complement of U union V in T. You can say that this difference is the complement of U union V in the set T. So it will be the intersection of the complements, complement of U in T intersection complement of V in T. Union, a similar argument here gives us complement of T in T intersection U union, because throughout we have intersections, so intersections will be turned into unions. Union this difference U union this difference V. We keep the first part intact. We don't want to do anything to this because it is in a form that is useful to us. T difference U intersection T difference V. Now union, what is this? Since T intersection U is actually a subset of T, if we remove T from it, nothing will be left. It will be the empty set. And for a similar reason, this one is empty also. Now, this if what I am going to write now in place of this, you find that unfamiliar or difficult to understand, you prove it. In place of this we can write T difference V intersection T difference, or sorry, not T difference but U difference V. You may get confused in the fact that here we have used an identity which looks like De Morgan's laws. Here, however, intersection has remained intersection. Note that here we are finding the complement of a union. Here this is not the complement of a union but rather the complement of a set in a union. That is an entirely different thing. So here the situation is not like De Morgan's laws. Anyway, I ask you to prove that this set is equal to this. It's very easy. There is no, you won't get any or, you will always get and. Okay, so that because of that it's very easy. So finally our T difference V looks like this. Union intersection U difference V. Okay, since T difference U and U difference V are both finite, you go back to our where things have started. What did we consider there? T is related to U and U is related to V. So that means T difference U, U difference T, U difference V and V difference U, these are all finite. From among these sets, here we have used T difference U, this is finite, and U difference V, this is finite. Now that means T difference U, this set is finite, and U difference V, this set is finite. Note that this first intersection is a subset of this because it is intersection. So this set is also finite and the second intersection is a subset of this. So finiteness of this implies this second set is also finite, and so their union is also finite. We get that T difference V is finite. Okay, for the moment, to show what we had as a consequence of our assumption, let us not just wrap this part up, let's keep this. Similarly, now if we switch V and T, then on the right hand side also we will have to do that. Now instead of starting from here, we use this final form. So in place of T we have to write V, and in place of V we have to write T. So V difference T union TV, so V difference T intersection, here in place of V we will write T. Okay, so just like that this one is also there. if we wanted, we could have proved this instead directly. However, it's difficult to guess the right hand side from the Venn diagram. So from the Venn diagram we saw what we could in a straightforward manner, and then ultimately as a consequence of our findings we have got this formula. Now here we will use the fact that u difference t is finite. This is now finite and v difference u is finite. So this is finite, and that's why again, since u difference t and v difference u are both finite, the set v difference t is also finite. So this difference is finite and this one is also finite. Thus t is related to v and hence our relation is transitive. Being reflexive, symmetric and transitive, this is thus an equivalence relation. Okay, now we are not being asked to find all the equivalence classes, but rather we have to figure out these two. We have to describe these two. This, by the definition of this relation, consists of those sets in S, and keep in mind that this means A is a subset of the set of integers such that or in fact let's just show everything. Is related to A. We haven't done anything here, we have just simply used the definition of this equivalence class. Now next we use the definition of the relation itself. Difference A and A difference this are finite. This is always finite. Why? Because it is a subset of this finite set. So regardless of what A is, whether A itself is finite or infinite, this is always going to be finite. So this does not determine anything. This does not say anything about A. This one does. Is finite. Can we go one step further? We can go one step further. Now note that if A itself is a finite set, then clearly this being a subset of A will be finite. Conversely, if this is finite, then A has to also be finite. How? Because if A is infinite, then removal of just 1, 2 and 3, which are finite in number, cannot make this difference finite. So for this to be finite, A itself has to be finite. So that means this equivalence class actually consists of the collection of all finite subsets of the set of integers. And okay, to write the things in a more simple way, let us invent one notation. Let 2z denote the set of all even integers. It's a notation that it's not something that I am making up now, but it's there in the literature. This usually denotes the set of all even integers. Then, so our second equivalence class is just that, the class containing the set of even integers. This time A has to be related to the set of even integers. So that means such that are both finite. This itself doesn't say anything more about A. For example, you can see that okay, does this really say something about A? The fact that this is finite tells us what? A itself cannot be finite because the set of even integers itself is infinite. So in order to make this difference finite, we have to choose a large A, and that too not just any large A. It's not even enough for A to be infinite. For example, if you remove from the set of even integers, say all the multiples of what I am trying to say, all the multiples of 3, say, then if say I remove this and this is my A, among the multiples of 2, which are actually the even integers, there are multiples of 3 also. For example, 6 is an even integer which is a multiple of 3. 12 is an even integer which is a multiple of 3, and you can clearly see that there are infinitely many such integers. So that means a actually is in, okay, this is not enough. I should have actually written 3k belonging to belonging to 2z actually, such that k belongs to z. This set is infinite. In spite of that, this is suppose our a. This difference is not finite. That is because there are infinitely many even integers that are not multiples of 3, namely the ones that are not divisible by 6. The even integers that are not divisible by 6 are not multiples of 3, and there are infinitely many such integers. So despite a itself being infinite, and despite the fact that this particular a is actually a subset of this, the difference fails to be infinite. So this a will not belong to this equivalence class. However, we can say one thing, that a cannot be finite. If you choose a finite a, then your situation is even worse. You cannot hope this difference to be finite then. So what I will do is that I will just simply leave this equivalence class here. From here, I urge you to say something more about a. So this actually is not complete. You somehow come up with something new. Maybe you will be able to say something definite about a, or maybe in fact you will be able to precisely say what a is or how a looks. For example, here we have said that a has to be finite, something like that. So I leave this incomplete here. Next, one thing that we can see immediately from here is that a will not be finite. So it's not like this at all. On the plane, R2 define a relation till via this rule a is related to b. Oh, now a is not just simply a, because we are in the plane, so each element is an ordered pair, is related to c comma d if and only if 3a minus b is equal to 3c minus d. Show that this is an equivalence relation, which will be very easy and describe the equivalence class containing the point 4, 2. And E, F belong to the plane. Since 3a minus b is equal to 3a minus b, we have a comma b related to a comma b itself, and so this is reflexive. Next, there is only 3 and that's all, nothing else. Yeah, 3a minus b. Which implies 3c minus d equal to 3a minus b, and so c comma d is also related to a comma b. Thus this is symmetric. Next, three c minus d is equal to 3e minus f. Is thus an equivalence relation. That's just it. You can see that this entire part is almost trivial. Now, the class containing the point 4, 2 is the set of all points in the plane that are related to 4, 2. That means (3x minus y equal to 3 times 4 minus 2, 12 minus 2 is 10. So you can see that the equivalence class that contains this point actually is the set of all points on this straight line. You know that geometrically this equation represents a straight line in the plane. So the equivalence class turns out to be a straight line. Let S be a non-empty set show that for any partition of S, there is an equivalence relation on S having the sets in the partition as its equivalence classes. This we will solve in the next video. However, before we end things, let's just see what this exercise is asking us to do. This is our set S, which is a non-empty set, and there is a partition of S into disjoint equivalence, disjoint sets. Equivalence classes are not there anywhere in the scene unless we have some equivalence relation. What is the definition of a partition? A partition is a collection of subsets of S like this, which I am not writing anything, just simply schematically showing that these are some subsets of S. A partition is a collection of some such subsets of S with these properties. Each subset is non-empty, that means each one has something in it. The subsets are mutually disjoint. If you take any two distinct subsets, there is no common element, and the union of all the subsets is equal to S. It's like partitioning a room into, or for example, partitioning a big hall into cubicles, if you want to think of it like that. All the cubicles or all the space contained in the individual cubicles Together they will give you the entire space of the hall or the big room. No cubicle is empty in the sense that in each cubicle there is some space, and different cubicles don't have anything in common. The walls are not considered to be, the walls, you can think of the walls as so thin that they don't take up any space. So that is the idea of partition. Now, this exercise tells us that we have to come up with some equivalence relation on this set S, such that once you find an equivalence relation, it will give rise to some equivalence classes, such that those equivalence classes turn out to be precisely these sets in the partition. That's what we have to do. So we will see this and other exercises in the next Lie algebra video, which will come on next Saturday. And tomorrow we will upload a graph theory video where we will learn about trees. So that will be all for tonight. If you want to say something about these things, you can write in the comment section below, or you can mail me here at this address. So see you in the next video. Until then, have fun with mathematics. And this is me, Lucifer, from a mathematical room. Have a nice night.